All right. So yeah, so we're gonna kind of so I have a couple things planned. We'll try to get through NLP stuff, but I also have an example of like convolution neural nets and like saying a little bit like Alvaro, like we were kind of just saying about like what do you do beyond just like having the neural network essentially, because it's kind of like you do the neural network, you run it, you're like, oh good, it did better. Let me change the optimization, tweak it a little bit and see it does better. That's not really super exciting by itself. Like I think a lot of times people will do convolution neural nets or neural networks and say, it did better. Now what? Like it just seems kind of empty. So we can talk a little bit about that. So I think I'll ask you guys, would you guys prefer to go into the NLP stuff that we didn't finish, or I can show you guys the neural network convolution example that I kind of put together. Which would you guys like to go? And we can always, if we don't finish it today, we can always extend it out to like another office hours. Any preference to anyone?
Are we gonna vote like a 1 or a 2 or something?
Yeah, we can do that.
Okay.
So maybe like a 1 for NLP stuff and a 2 for the convolution direction. There's actually a split vote. It's kind of split there for a second. All right. I think most people had 1 up at one point. So we'll go over the natural language. I saw Christine come up too. Okay, people turning on the cameras for like half a second to vote. All right, so we'll just go over NLP stuff first. I think we've got through most of it. So hopefully we have enough time then to kind of show you guys a little bit of like what that project looks like that I mentioned. So I'm sharing my screen again. Cool. All right. Sorry, I have to like reorganize. Zoom just likes to move my windows around when I share my screen for some reason. Okay, so let's go into NLP. And we talked about, let's see here. We talked about intro to NLP, talked about what natural language processing is. We talked about actually processing those texts, like for example, like stop words, stemming, lemmatization, all that stuff. I think we talked about, did we talk about feature extraction, bag of words, TF-IDF, word embeddings? Maybe like very slightly, does that seem right? So maybe it's a good place to start.
I know that we didn't get to word embeddings, but
yeah,
right.
Mm-hmm. Yeah, that's definitely right. So let's kind of go through a little bit, and then like if it's starting to look familiar, you guys just give me a thumbs up. Yeah, we got over this, and I'll skip right over. So I mentioned about features depending on the task, right? If you're doing different things, you have to think about what features you care about, right? I like to say like NLP is kind of like very informational dense, right? Informationally dense is that there's a lot of stuff you can get from it. And so we need to make sure we extract those proper features so we can focus on what our actual goal is. So like I mentioned, I think bag of words would be really useful for like overall like sentiment, for example. We would, here, I'm trying to actually remember what this thing is. Oh, I think I did we talk about this right here? I think this looks familiar now. Yeah, okay. So bag of words, so you can think of like the whole document, right? So moving on to that. TF-IDF, this is basically our frequency. I think I showed you guys a little bit of a, like I drew out a little thing with like the different words and stuff like that. So was it term frequency, inverse document frequency, TF-IDF? I think I've heard someone pronounce it once. I've never heard anyone pronounce it after that, like TIF-diff or something, but I just call it TF-IDF. So anyway, there's those parts. And then the last one was word embeddings, which is the one that I think I kind of mentioned, but then never went into full detail. So that's kind of a useful one to talk about. All right, so let's talk about that then. And this already assumes like you processed it, you have gotten your tokens, you've done your stemming and lemmatization and all that stuff, okay? And so one strategy, which is I think is one of the coolest things in embeddings. And so we'll kind of just go through this. Oh yeah, I think I showed you guys this picture, right? About like this space. So you can think of an embedding as just essentially a vector. And it's a vector in some dimensional space. And basically it's to essentially, we call it embedding because it's embedding information into a smaller, usually a smaller space than what you started off with. The bigger space is basically just saying like what the word is. So you can imagine a vector that's like, let's say you have 2,000 different words or 200,000 different words you use in your whole like corpus. You would have essentially like one hot encoding of saying, oh, this word was used a 1, 0, 0, 0, 0, 0, 0, 0. And then it's like, oh, this word was used. So 0, 0, 1 representing that word. 0, 0, 0. So it's a very large dimensional space, which makes it really hard to actually do any training because of the cursive dimensionality for like a machine learning. So what we do, we can actually reduce that space with embeddings to say, well, let's kind of make a shortcut. And this is where I mentioned about like man, woman, king, and queen, where essentially like these like, I think of like analogies with like, I don't know, back like standardized testing. If you guys ever like came across that, where it's like a man is to a king as a woman is to blank. It's like, oh, to like queen. That's kind of the relationship that's here. Note that this is based on like gender, but it could be on anything really. And in general, you tend not to really know exactly what the machine learning algorithm is going to find. So that's kind of what the idea of embedding is. It's the real reason why it comes down to like why this works is basically this idea of the distributional hypothesis, which basically means is that things that are closer together, like in a vector space, are more similar to each other. So it's kind of think a little bit about clustering. That's kind of the idea of clustering as well. And that's kind of what's going on here, but it's more in depth about saying like the relationship from in the space versus just saying, oh, these are close together for whatever reason. It's like, oh no, these are close together because we can actually transform, like essentially move the vector in that space and actually move the whole direction. So again, like this man to woman, king to queen, if we move in the same direction, we shift everything into like, you know, from a male to like female. Make sense? I know it's kind of abstract, so feel free to like say, I don't understand it, or, you know, like, can you go into further detail? All right. So just kind of moving on. There's some really great resources, and we'll go over some of these right now. But there's also like this embedding crash course from Google, which they actually have a machine learning crash course. I don't know if anyone's come across this at some point, but they actually talk about a whole bunch of things. You can see a whole bunch of things that you guys can probably learn, like either review or kind of learn a little bit of extra stuff. For example, this testing debugging, I just talked to people about actually what happens when your neural network's not doing very well. Actually, is a very quick thing. It's not super detailed. Like you're not gonna learn a huge amount. Like you're not gonna become a master by taking like, you know, this free, like it's free, right? It's available online for free, but it's helpful and stuff like this. But we're gonna focus mostly on these guys. So I'm trying to think how I want to approach this. I'm actually gonna skip word to VecGlove for a second and just kind of show you guys what embeddings can do. And so this set of Kaggle lessons, it used to be on Kaggle, you could do, where is it, Learn? Oh, courses, that's what it's called now. It used to be, yeah, it's called Learn. It used to be part of this like set of learning stuff. And these are like, again, these are, if you go on Kaggle, you guys know more than enough to understand all of these things, and you could probably just learn a little bit extra stuff. For example, we don't talk about geospatial analysis, but you guys know enough now, you could probably look at this and understand pretty much everything you need. It used to be in here at some point. I think it was under feature engineering. For some reason, things had changed, and I don't know why. But I have it all, like I listed out here because the notebooks still exist. They're just not part of the Learn part. Kind of like going through a little bit like what this is, these notebooks, and you guys can go through it yourself, like with more detail. Essentially what happens is that you have a user and a movie, and then saying what the rating is for that movie. And basically this is the exploration of a few notebooks that kind of go into that detail. So can we make that prediction of saying, hey, like how well can we predict what movie they'll like? So if, for example, this user liked these movies with these ratings, and this user liked these movies with these ratings, what's this new movie that maybe user B never saw, but user A saw? So like what would we expect that rating to be? So basically you can think of it like a recommendation class. And what we can do is actually use embeddings. So what's kind of cool about this is that when we build this embedding, and we'll go into exactly how we can build these things, but we can actually build this thing into like essentially a smaller dimension, vector space. And you can kind of think of it like, eventually you have like, for example, this vector here, which is essentially 1, 2, 3, 4, 5, 6, 7, 8 different numbers. And those 8 different numbers in some ways kind of represent some aspect of either the movie or the user itself. So I think in this notebook in particular, they kind of say like, well, what does it mean to say 1.62 in this direction? Like this might, for example, mean that this is like, oh, this is a comedy versus, you know, a tragedy or something like that. Or like how funny the movie is, you know, which is not directly related to the rating, but you can start seeing where people like certain movies. Like, for example, some people really just like comedies and that's all they like. You'd see the certain pattern in there. And so it starts pulling out those patterns in here. So this number might represent, for example, the larger this number is, the funnier it is. And then as we get closer to 0, it's like less funny or serious and whatnot. And then maybe this next one, for example, is like, how much is a romance movie? So you can imagine a romantic comedy would have high numbers in this value, in this value. I'm saying like romance in like comedy as if like that's what it would actually learn. We don't know. Like it could end up being something completely different, or some value we really don't understand exactly what it represents, but we'll start seeing patterns out in that direction. Does that make sense to people? Like how this kind of, like what these numbers would represent for a movie? Cool. So what's kind of cool, if I gave, you can also use the user now to represent, be represented by these numbers. So if I gave you now, like we can imagine a movie saying, oh, this is how funny the movie is, this is like how romantic, you know, this movie is, and so on. What do you think I would mean if I had the user be represented by this vector with these numbers? What would those numbers represent? Like pretend this is the user's vector, and I have this in the movies, it's like about how like funny the movie is. What do we think like this number for the user would represent? Like how would we translate that? I guess. Yeah, it's subtle here. So usually what you can think of this little part of the vector here for the user is saying how much they like comedy movies, how much they prefer these things. So what ends up happening, we can actually take a dot product of the user and like the movie and actually determine then saying, well, if you do a dot product, you're basically saying how closely aligned are you with each other? If you are like, imagine the perfect value is like, it's perfectly aligned with each other, you would have like essentially on top of each other, meaning that essentially it's the same data point. So if you like comedy movies and stuff like this, you would actually, what's it called? If you like comedy movies, you would have that value very high. So you would match really well. You would have a high output from your dot product, for example, of a high comedy movie. Does that make sense? It's like if it's movies like rated at like 10 or whatever, it's like, oh, and you had like a 5. It's like that means those numbers multiplied together would be 50. You're like, oh, that's a pretty high number. Versus if you had, you know, 5 for your how much you like comedy, and like it's 0, meaning it's not very funny. 5 times 0 is gonna be 0, so you're gonna have a lower number for that value. Does that make sense? Like how those match up? Okay, so that's the idea of what we want from our embeddings. So then it comes down to like, well, how do we implement this? There's a whole bunch of ways we can do this, but one kind of fun way to do this is actually using like a neural network to actually try to create this embedding and stuff like this and implementing it. So basically, I'm going to kind of skip around a little bit, kind of moving through, because they show you like how to build this and stuff like this. I think you guys, if you want to, can kind of go through this yourself. But I have a little example of like this, for example, for, let's see here, word to vect. And I think this is a pretty good example of like what this would look like. So essentially what happens is that you can have like an input as like basically saying what like, and kind of going back, we'll go with movies, is what the ratings of the movies are. And then you have this neural network inside, you know, have some hidden layers. And then on the output, on the end over here, like over on this side, is literally just saying, you know, what the rating of that movie is. And what it is, you basically try to train it so that, hey, take these values, these inputs for all this different data, pass it through the network, and try to reproduce the same exact output. Or sorry, it's the same exact input. So they're basically symmetric. And what happens there is essentially is that this inside part, which you will see, I think this is from the curriculum itself, is this is 10,000 and this is 10,000. And then inside here, this hidden layer, in case there's one hidden layer, is 300. The idea here is that you now have a smaller vector space, right? Because each of these numbers basically represent a number in a vector. You now have a smaller vector space that's going to basically condense information into this smaller package form. Does that make sense to people? Like if you can kind of think about this, it's like if we have all this stuff and we're able to reproduce the same stuff, then that means since this thing is only determined by these, like this last hidden layer, that means this has to encode information about it from the beginning. So we're basically like condensing that information, figuring out shortcuts so we don't have to use as many numbers. So that's what's going on here. And basically you just train this over and over and over again. So it's kind of a cool way to basically like create this new, what we call this right inside here is the embedding itself. Essentially, this is our vector. And now I said this with movies because we're going to look at this in a second, but this can also be done with like NLP, like words. So for example, you can say, okay, each of these vectors right here is a different word. So imagine like this, for example, is ant, aardvark, barber, you know, all that stuff, and all the way down to, let's say, I don't know, like let's say this is like bumblebee. And this right here is like, okay, this is saying this is the word bumblebee, and it needs to be trained in here, passed through the network, and then output, and this should give ideally 1 for bumblebee and 0 for everything else. It's never going to be exactly right. It's going to be slightly off than 1, right? Because it's always going to have like some like, it's not going to be perfect, right? And so you do this for every single word you have. And the idea of there is that you're actually teaching the context of what those words mean into this hidden layer. So the idea there is that it basically, because this is so much smaller, it has to condense some of that information and do shortcuts so it can kind of essentially learn context. And by context, what we really mean is that similar words show up in similar places. So for example, a fluffy dog is a great pet and a fluffy cat is a great pet are 2 examples of the same exact thing that happens, right? Like, are 2 examples of basically the same thing, but just 1 word changed. So that means, and they both make sense, that must mean dog and cat must be relatively close together. They're very similar in context, basically by the fact that these words can be used interchangeably, more or less. Now, obviously, in a different sentence, a cat and a dog are going to be different things. For example, like, you know, the dog barked at the male person. You never see a cat bark at the male person. Like, that's not a sentence you come across very often. So therefore, like, cat must be at least somewhat different from a dog. Does that make sense, like in the context? Okay, and essentially that's how we can train this stuff. I won't go into the whole details of like how you implement it. I just kind of want to show you guys what that concept is. Glove is kind of similar to this, except without using neural networks, you can actually do this with essentially these matrices called these co-occurrence matrices. But the idea there's the same thing where basically in the end, what we want to be able to do is take essentially this, like in this case, this word feature and this feature content and create basically this word content. And so the idea is that we really want to build up this feature content, what's it called? This matrix itself. We have to figure out what's going to be the best thing to multiply this word feature to feature content. And basically we're trying to build up this content right here. And the content is just going to be based on saying how similar those words can be interchanged with each other. And so if we know this and we know the other thing, we can figure out, like, just guessing essentially and trying to optimize and trying to get as close as value as possible where we multiply these 2 things together to actually get this word's contents. Okay. Does that make sense? Like the concept there, like how we can essentially design something here that can make this thing work. It's kind of like algebra, where like if we know this is 5, or let's say we know this is 15 and we know this is 5, then you can figure out what number you need over here to get close to 15. And it gets a little more complicated because we're never going to get exactly it. So like you can imagine, like if we had 15 and 5 right here, and then we could say like, let's try 2.5, you know, it's like, well, that's going to be close, but not quite, right? It's going to be like 12.5. And it's like, okay, let's try like 3.5. You know, it's like, oh, that's not quite right, you know, but it's close. That's kind of what you do here is that essentially you're building up this entity that is going to maximally like recreate this equal sign over here. Does that make sense? Like the concept on that? Okay. Again, like what does it mean by this content versus words? Essentially what it means is like, oh, how often does this word show up in the same sentence or within the same like 5 words? So if this first word, for example, is like dog, right? You might have like fluffy, pets, you know, anvil, and I don't know, car. And for that dog, maybe anvil like shows up like almost never, right? So there's not much context. I might have been saying content, I'm so sorry, meant context. Your context of saying, oh, that's where dog occurs. So dog like frequently is accompanied with fluffy and pet, but almost never with anvil and sometimes with car. So that's like the context there. And then what we want to say, okay, this is the word, and then we're going to build up these features, which we don't know what these features are, essentially. Like we're trying to build this up. And we basically are trying to recreate this features context here to say, well, okay, what if we can adjust and make this feature happen and try to optimize when we multiply these together, these 2 matrices together, we get back the words and context. So that's the idea of what we're trying to form. And essentially what we're doing essentially is taking this, these 2 values right here, this row and this column, multiplying together and putting it, trying to get the value that's as close as possible to this over here. Okay. So again, it's like algebra essentially, but a little bit like based on data, if that makes sense. Like we actually don't know what the real solution is. It's just based on whatever data is on here. And there might not ever be like a real solution, but it might be close enough. And that's really what this part right here, if we can get our embeddings. Okay, does that kind of help a little bit? Like, I don't know if that like made it more confusing or less confusing. Any questions or comments about like what's going on there? Yeah, okay. Just kind of know essentially is that the algorithm that's building, when you build up Glove, which in general, you don't have to build up this embedding. Usually Glove has already been pre-trained for you. So you can basically, someone's already figured out how to optimally create this matrix. And we're using that solution to do our embed, to basically use that as our embeddings. But in the idea of it is that they were using essentially figuring out like, well, what features would make these numbers work out, and that's where Glove is coming from. Okay, so that's a different process though than like the skipogram model. So note that these are two different like processes, but they still produce in the end some kind of embedding. Okay, cool. All right, so like what can we actually do with this? That's where we actually get into these kind of guys. So one is the actual Genism. Have we came across Genism library in the curriculum? I don't think it's in there, no. All right, so what's kind of cool is that you can actually use this word2vec that's already been kind of trained and say, hey, here's our data. I want this kind of size of our embedding. And then basically these other things are essentially like this workers, this min count, basically is for training. And we can say, go ahead and train off of this model and create essentially our embedding from this. And what's really cool, then you can actually do some exploration with that embedding, which actually gives you a lot of information about like how these words relate or whatever you're looking at. For example, the movie, I think example is a really good one because I think most people wouldn't expect you could actually determine so much about a movie just by looking at people's ratings and knowing nothing about the user, knowing nothing about the movie itself other than the literal title, just because you need a label, and just seeing how those relates together. So we'll kind of look at that next. So let me go ahead and open up this guy. Okay, so if you guys want to know more details, I think these two notebooks are really good at actually talking about essentially these things, but in the context of movie, like movie ratings. But it's the same concept. It doesn't really matter what it is. You just need something to say, oh, this thing is similar to the other one. So assuming we already have these embeddings already made and stuff like this, and I think in this case, we actually have embeddings that are a size 8. We can look at saying how similar these different vectors are to each other. And these vectors are going to represent those different movies. So for example, you see Toy Story vector, Shrek vector, and basically you can see distance Euclidean. Basically they're saying how far away are these from each other? And this can help you get an idea of like how far away things are. It's like, that's really cool. Now I mentioned like you can do something like a dot product. Turns out dot product's not super, like can have some issues with it. So actually turns out cosine distance is generally better. And essentially cosine distance, if you like, does anyone give me a thumbs up who knows what cosine distance is? Like could explain it to me like in like a minute. That's okay. Cosine distance, all it is essentially you have a vector, remember it's just an arrow, right? Or you can think of a point in vector space, but it's an arrow. And then you have another arrow, right? Another vector, and you say, all right, they start from the origin, the middle of the vector space, and then goes out to wherever in its space. And the cosine distance literally is just saying how much of an angle is it between these two vectors. That's essentially what cosine distance is really talking about. There's some reasons why this works better than a dot product, where literally you're taking these products and multiplying together by basically I hope I'm not getting too advanced for people, but projecting this vector onto the other one and saying how much of that vector overlaps. There's some reasons why this doesn't work well. And part of it's because you can have like a negative vector where they're pointing in different directions, but their dot product looks good enough. Cosine distance kind of encapsulates that a little bit better. So what's nice to just know that your cosine distance goes from -1 to 1, right? So we're just saying like how much of a difference it is. -1 is basically saying it's pointing the opposite direction. It's literally the like different, I'm trying to use my hands to do this, like different direction versus like something that's really close together, almost 1. That means they're almost pointing on top of each other.
Okay. Is the cosine distance the cross product?
No, it's slightly different. I think it's built around the cross product. No, it's not built around the cross product. I'm sorry, because cross products don't work with every dimensional space. It only works for 3 dimensions, and I think 7 is the next one that it works with, that you can define a cross product, which is why we can't use it. So because we have, whatever, dimension, but cosine, there's always an angle between the two, but there's not necessarily an orthogonal. For the record, when you do a cross product, you're looking for an orthogonal direction, and there's not always one that exists for different dimension sets. Good question though, because sometimes people relate cosine with cross products. So anyway, they're measuring basically Toy Story with Shrek and Toy Story and Exorcist. And what's kind of interesting is that Toy Story here, actually, I'm actually surprised by this. I wonder if they say this. It looks like Toy Story and Shrek are actually a little further away from each other than like Toy Story and Exorcist, which I'm kind of curious now why this is true. I'm trying to see if they actually talk about this. But the point is that you can actually see how close and similar they are. So which movies are similar to Toy Story? Which movies fall right between Psycho and Scream? Why is the cosine commonly used for it? Oh. I just want to make sure I understood this right and I didn't say something. If the vector points in the same direction, the cosine similar is 1. From the opposite direction, -1. Yeah, oh, weird. Okay. Apparently, according to ratings at least, Toy Story and Exorcist are more closely like each other than Toy Story and Shrek. I don't know why. That's an interesting one. I'm kind of curious now. I wonder, okay, I'm just going to speculate real quick. This is where, for example, like why it's really interesting. Like, well, what does that mean that they're close together? This could be literally because maybe people who've watched both of them are similar ages, so they have similar tastes and stuff like this. So they're similar coming out from there. But I'm actually really surprised that that came out. Anyway, moving on. But Genism basically allows you to, or Gensum, allows you to build up these embeddings really quickly. And what's kind of cool is then you can say, hey, what are movies that are close and similar to Toy Story, or like this label? Say, oh, there's some space in here. And say, what movies based on the user ratings are similar to Toy Story? And note that whenever I say movies and ratings, just think, you've learned this for NLP, think words for movies, and for ratings, think of it as being like, how common are other words near them? So that's kind of like that context. But in this case, the context is built off of user ratings. So you can see here, similar movies that are similar to Toy Story. Toy Story 2, Toy Story 3. Makes a lot of sense. Finding Nemo, Monsters, Inc., Bugs Life. I think you see a pattern if you know these movies, right? They're Pixar movies, right? And that kind of makes sense, is that if you like one Pixar movie, you tend to like other Pixar movies. Also, you can see Toy Story 2 is Toy Story 3. Those would be kind of similar to people who would rate Toy Story. So this, I think when you look at this and think what these are similar to, it makes a lot of sense. You can also see the Iron Giant here is kind of like the first non-Pixar movie that comes up in this case, I think. Yeah, first non-Pixar movie. But like, if you said that, and if you're familiar with the Iron Giant, you're like, that kind of makes sense. Like, I can see how these are similar, why they would be close. But you notice that's a little bit further away than something like Bugs Life versus Toy Story. Okay. So anyway, that's kind of like what you're building. And one thing to know is that when we built up these embeddings, we don't know what the word, we just have a label. It says Toy Story 2, but it's not training off of Toy Story 2, like the word. It's not training off of, oh, we know information about these movies. We're not even learning information about the users themselves. We're just saying, we have a bunch of users, we have a bunch of ratings. This is what basically produces this context. Okay, does that make sense to people? Okay, it's important to realize that too, in case you thought like there was some crazy thing being hidden here. So you can see a little bit like there's some really interesting stuff you can do. And this is very similar to when I talked about these embeddings up here, where you can kind of like shift the vector down and you can get into these new spots. You can actually do something like analogies where, for example, you can take like Scream equals Psycho plus something else, another movie. Like what would that be? And so you can actually check that out. And what's kind of cool is that if you actually try this, let's see what they end up pulling up. Oh, they just showed what's similar to Scream, similar to all these things. And what you kind of see is that I think they kind of say, oh, Scream is a comedy and Psycho is like a horror film. So what you end up getting is things that are like Scream minus Psycho are essentially kind of like these, a little bit of like silly movies, like kind of like there's kind of, gory kind of like horror movies, but also kind of got a little bit of like comedy kind of like camp to them and stuff like this. Then you start getting these weird directions like Charlie's Angels and Mortal Kombat, which again is interesting by itself. I could kind of explore a little bit deeper into that. But you can see a little bit like I mentioned about like analogies. You can see, for example, Brave to Cars 2 to Pocahontas. And I think they end up finding, what did they find? That's like the missing part of if Brave is to Cars 2, what is Pocahontas to? And I think in this case, they find like a kid, Arthur's Court. And then you can talk about saying, well, why is that difference in there? So there's a whole bunch of detail in here that they kind of speculate what's the reason for this. So it's kind of a fun thing to do, which again, they do this with movies, but you can totally do this with like words by themselves. Okay. So that's really cool. But I think this is where like people say, okay, this is nice, but like, what does that mean exactly? Like, how can I visualize this? And that's where visualizing with TISNE or TSNE, I usually say TISNE, but this is where basically it's like we have an 8-dimensional space. So if you imagine whenever we got these vectors right here and they say, hey, there's some vectors in some eight-dimensional space that I cannot comprehend. And these vectors are close together, right? Well, there is some space that we can kind of like visualize. If we could see that space, we could actually see the points and where they lie. Well, obviously, I don't know about you guys, but I can't visualize in 8 dimensions. Like that's not a thing I can do. So what we can do is actually kind of reduce that dimension down. But the problem is with reducing the dimension, we don't want to just project things down because then we lose information. Think of it like if you looked at a shadow of something, can you build up the 3D image? It'd be kind of diluted and like it might actually be messed up and you might think things that are close together that actually aren't close together. So think of like if I had a shadow of my hand and a shadow of my hand on top of each other and they looked downward, it looked like my 2 fingers would be like crossing like my ring finger here, or my ring is really close to like my fingernail. But in reality, it's really far away just because you're looking down on it. So that'd be an issue. So TISNE is a kind of a cool way of doing this. Essentially, I won't go into the mathematics, but basically you're essentially making a manifold and you're creating a thing that's going to map onto this lower dimensional space. But what's cool about TISNE, and the thing that you really should know about it, is that it preserves not the shape, but preserves the distance between different points as best it can. So you can take something like 8-dimensional or even higher and reduce it down to 2D. Sometimes you see 3D, but usually 2D. And so I'm not going to go through the code a bit because you guys can definitely read through this a little bit yourself. But no, this is actually built into sklearn. And you can actually see here is that this right here is actually all the different movies that this person had put together as data scientists and not projected it, but basically created TISNE using TISNE, creating a 2D graph. And so what you should interpret from this is that every point in here is a movie. And these points in this that are close together are literally close together in 8-dimensional space. And that's the way you can interpret this. And so what's kind of cool is that you can actually investigate. So they actually go into here, it's like, hey, let's highlight anything with Harry Potter. So basically Harry Potter, 1, 2, 3, and so on. And you can see they're all really close together in green. That's a good thing. So they zoom in a little bit and you can actually see here, hey, all the Harry Potters all hanging out together, right? Which is what we want. You'd expect Harry Potter to be very, very similar to each other. And what's kind of interesting though, if you look a little bit off to the side here, you notice that these are not Harry Potter, but they're relatively close. And if you guys can read that, that's actually Hunger Games, the different movies. And when I say that, I think hopefully you kind of go like, yeah, that kind of makes sense that Hunger Games is relatively close to Harry Potter. It's not the same thing, but you can kind of see, and you can talk about like, are these close together? And again, they're built off the ratings, but you can kind of see if you look around here, you might find other like teen focused movies, kind of like series kind of thing. You can kind of probably focus around that and probably figure out like, oh, some other movies would be here as well. You can actually check that out. So that's kind of like looking at specific parts, but what's really cool, I think, about TISNE is you can look at the global structure. And when you do this, for example, if you have different genres, like in the movies and stuff like this, you can actually say what things are very similar to each other and where do they appear. And so it's kind of cool, for example, they highlight all the documentary movies. And so you see the documentaries are basically on this right side, and they're still scattered because some movies are going to be very different from others, even though they're the same genre. But you can see they kind of cluster over here. And then I think they go into like comedies and romance movies as well. And so they actually, I know this is kind of hard to see. Hopefully you guys can see it. The color is not great, but there's comedies in like this orange, yellow, drama is in green, and red is in romance. I don't know if anyone's colorblind. I apologize if anyone's colorblind because this is probably not the best visualization, but you can see here, like, for example, drama in green is definitely clustered around here. But then we also have like comedy, like kind of on the other side of drama, which like, if you think about it, like, that kind of makes sense, right? You wouldn't expect common and Dramedy necessarily to be close together. They're kind of in some ways opposite of each other, right? But there is some kind of leakage between the two. And then you can see romance here, which is my favorite. It's just everywhere. Like it's just over here, over here, over here, over here. And you can see some places are really close to dramas and other kinds are kind of close to comedies, which kind of makes sense. You kind of have this romance comedy, like that would kind of mix in together. And so this is the kind of idea, like how you can take something where you really don't have any structure other than saying, what is the context of this data set? In this case, this was movies and ratings, but you could just say, instead of movies, talk about words in the context of them being used, how often they're used and how close they are to other words. So like think of like the 5 most common words around another word, like using that as a context, is that you can actually build these structures in here that give you global, what's it like, looking for pattern recognition. And you can see, for example, and this is the idea of like sentiment analysis, is that you can say, hey, like, well, these words are being used frequently for this kind of direction. And you built this all literally from the embeddings. And how you get those embeddings, it just depends on what you want to do. But once you have those embeddings, ideally they encode some information that you can put in. And with Tisneans in particular, it's super useful to actually see where there's higher dimensional space, how we can actually look and see what things are close together. So it gives you a little good quick visual and quick way to explore it. Okay, cool. Is that any questions or? I know I went through this really, really fast, and like, I really recommend like reading through these sets of, like I think I have this on the repo, right, on NLP and embeddings, looking through these 4 different notebooks. They all connect together. But if you start off with embeddings intro, I think it gives a good perspective of like what this looks like and what you can do with it. And again, it's dealing with movies, but you can extend this to whatever embeddings you want to really talk about, especially with NLP. Yeah. Cool. Yeah, this is another graph of Tisne. So I kind of mentioned it's like PCA is used for dimensional reduction. It's different from PCA. No, PCA is looking for variance change, where Tisne is looking for how close things are together. So just kind of know there's a little difference in that the way they work, but they do similar outcomes of like trying to reduce dimensionality. But they're super useful when you're trying to look at distances because they identify that stuff. Yeah, so I kind of linked over to dimensionality reduction as well from like Tisne. Yeah, cool. And I mentioned transfer learning here. Basically what's nice about this, I kind of mentioned this at the very end, because once you have an embeddings, you can use those embeddings that are basically like already trained on very large corpus or like a very, very large amount of like data, and just use the embeddings that have already been learned from another corpus. The thing about that is be aware that you are inheriting whatever that data set already had. So if that data set had some kind of bias in there, you're going to inherit that bias in there. So being very aware of that stuff, especially if you're like specific data set that you're exploring and using, you want to make sure that like it's at least similar to the overall data set that the embedding was first created from. So that can be really important. For example, if you have something on Twitter, for example, or like different communities and stuff, like the way they talk and stuff like this, they might use context differently. For example, if you have a bunch of teenagers or people who are like African-American, for example, there might be different things that are being said like in speech and stuff like that, that will not translate well with the original data set that you started off with, or that was trained for that embedding. So always be aware of that kind of stuff. And then what's kind of nice is that it's very comparable to like CNN transfer learning, which I know we didn't talk about, but maybe we can talk about that in the future, where basically you can just consider saying, well, okay, how similar is my data set to the original data set where the embeddings came from? And if it's relatively similar, you can probably just use them directly. But yeah, that way you don't have to like train a huge amount of data. So cool. All right. That's kind of all I had for NLP stuff, at least for what you guys would for the mod project and stuff like that. I will mention I didn't get into sequence to sequence, but I think I'm going to save that a little bit, maybe into like when we finish mod 4, because I think it's a lot to handle all at once. But if you're curious, you can definitely look into it a little bit more with like RNNs, recurrent neural networks, and LSTMs. Know that those get a little more complicated, trying to do certain things with that. But I think all of this stuff right here from embeddings, feature extraction, should be more than enough for you to be able to do a project like what you have for mod 4.
Question.
Cool. Yeah.
Since you mentioned transfer learning, on the project for the pneumonia X-rayed, identify whether it's pneumonia or not. Are we allowed to use models, that existing models, and just use transfer learning on them?
Yeah, I allowed is a strong term, making it sound like, you're not allowed to do certain things. Like, yeah, I would suggest, and this is actually what I'll kind of go into now in a second. I know we're got 5 minutes left, so maybe you can spend a little bit extra time. But there's no reason why you can't. I'm not going to stop you saying like, oh, don't use transfer learning. I think that's important because like, why would I stop you to use transfer learning? Because that's what you would probably use in the real world, like, right? But I would say starting off with a simpler model and trying to understand that first, and then try to evolve forward, and then try transfer learning. I think that will be more fruitful versus like just going with the big guns and say, hey, this model already works. Let me try to use transfer learning on this and just run with that. And it's like, oh, look, it works. And you're like, cool. It doesn't really help you in understanding like the data and understanding like, what this process looks like, especially for this first project or this project in particular, where you might be the first time you're doing image recognition. So that'd be my advice. But yeah, definitely go for it. Like if you're like, cool, like I think I can do this, like, yeah, I definitely love to see that in a project. Cool. All right. Other question? I think
yeah, I have a question, but it's maybe unrelated to this. So, okay, cool. So my question is, what's the timeline going to be like for Capstone?
Yeah, good question. So I don't have the dates up on right now. So you guys are doing Mod 4 project this week and then next week, where you guys are working on your project. So at this point, hopefully you guys have already started a little bit of data exploration, have your repos kind of going through and stuff like this. Hopefully kind of, I would say, if you can get to the point of loading and doing some exploration by the end of like tomorrow, that would be a good spot. And then we have all of next week, right, for your Mod 4. And then we have break week after that, which break week essentially is just like, there's no courses, there's no like new material and stuff like this. But when we come back from break week, you guys will do your Mod 4 project assessments, hopefully within that very first week. And this is where I'll tell you about the Capstone kind of timeline. I want you guys to finish, my goal for you guys is to you guys have done with your assessment before the end of Friday of that week we come back. So that way you're not working on that second week, and you guys are all nodding like, yes, like I'm sure you guys are aiming for that too. So that's my goal for you guys. And I want you guys to know that, because then we can focus on Capstone. So when we come back from break, there isn't any more new material in Mod 5. Essentially, Mod 5 is work on Capstone. That's literally what it is. And so the timeline kind of going forward, and I'm just going to pull up my calendar off the side here, is we'll start Capstone that week we come back, which is September 14th, is that Monday. And we have, I'm just going to go through a little bit dates. I think your graduation date is November 6th. So basically from that point, September 14th to November 6th. November 6th is when you should already be done with all of your Capstone project, do your assessment for your Capstone, have all your blogs, and you graduated. Like, so you can see that's a huge amount of time, and like what happens in between. This is where like when you guys come back from break week, I'll kind of talk about saying where I have like little soft deadline dates of being like, oh, you should have your data set picked already. Okay, you should start doing you should have had your exploration done at this point and move on to like the analysis part and like your modeling. And that's where I'll kind of like give those little soft deadlines. But in reality, you have all that time to do the whole Capstone. I've had students, not that you should do this, wait until like 2 weeks before Capstone and say, I finally figured out what I'm going to do for my Capstone project. Those are not good. Those are not good times for them at all. They are stressed. They try really hard. They don't usually make it on that specific date. We work with them and stuff like that, but I don't want that for you guys. I want you guys to graduate, not because I don't want to hang out with you guys and see you guys all the time, but when you're graduated, then you can think about getting your job. You don't have to think about finishing up this Capstone and looking for a job. You can focus on just getting a job and working with the career coach and everything. So that's kind of my goal. The timeline is really loose. You guys kind of know me at this point. I'm not really strict on being like, you need to have these specific things to move along in like the Capstone or a project, but I'll give you guidelines of like where I think you should be at. Hopefully that kind of answers a little bit, Jessica. Yeah.
It does. And thank you. And I have a follow-up question to that. So then let's say if we finish our capstone early, at what point do we start working with a career coach?
Yeah, so that's a good question. So the way it works in the Flatiron system is that when you are 5 weeks from when you're supposed to graduate, as long as everything's kind of turned in, essentially, like you haven't like disappeared and stuff like that, we basically trigger internally saying, okay, you went from your educational coach, which is Dara. You guys have met Dara before, and you'll be assigned a career coach, and they'll work with you through up until you graduate, and then past that until you're basically working to get a job. So that's kind of like the next step. And that, I think, so 5 weeks before that is the end of September. So somewhere around that time would be like when you would start looking at career coach stuff. Cool. All right. Awesome. All right. So I know we're at time. Let me ask you guys, would you guys like to go an extra 10, 15 minutes, or everything is too long? I see a thumbs up. All right. I don't see anyone else doing thumbs up, so I don't know. Maybe you guys are like, that's enough for today.
That feels like a good stopping point.
Yeah.
That's just I know there are 10 of us here, so that's my,
Hey, I'm going off of the people who give me responses and stuff. So tell you what, I will save this for next time. But if you do want to look at what I am talking about, or what I will talk about next time, which is basically kind of going a little bit of image recognition, I did have you can actually find this repo pretty easily. So I'm not really concerned like, oh, I'm sharing this repo. There is from Udacity, there is like a traffic sign recognition project that they do. I think it's kind of, I think sometimes we give you guys a little more work than what they're doing, because it's not data science, I guess, but whatever. But building a traffic sign recognition, I'm going to show you guys a little bit of this. This is a little project I had been working on, just kind of playing around with, but I want to share this learning branch, which basically, I'll just kind of quickly look at it and then I'll tell you guys what we'll do, and then we'll end it here. If you want this, I'll share it in the chat right now. That way you guys can pull it up as needed.
I'm happy to hear about this too, if this is what you're going to tell us.
Yeah. I don't want to, does anyone have to go? Just give me a thumbs up if you yeah, I really have to go right now. That's okay. So I'm not going to go too much longer. So if you have to head out, it'll be on the recording and everything. But I'll just briefly say it and we'll go into more details. But basically, it's an image recognition thing, and I'm going to show you guys a little bit of what this process would look like. Loading the data in here, you can see the example images and stuff like this. And then this is where people say then I just go into modeling, and it's like, no, there's so much more you can do. So for example, I do a histogram of the actual classes, but then I kind of go and say, well, how would you solve this without without deep learning convolutional neural nets? What would you do? And that's where I kind of show a little bit saying, hey, let's look at the brightness of different images. We kind of talk about that. What if we actually use a random forest to actually try to do this classification? And it turns out this actually does pretty decently. Not great, but better than you might expect. And then we actually show, hey, let's actually do a convolutional neural net. And I'll show you a little mistake that you can easily do. For example, not one-hot encoding, and where you think you're getting really, really great results, but it turns out you're actually learning off of the actual labels and stuff, which is not good. And then actually showing you what this model looks like, actually doing one-hot encoding, doing it properly, iterating over more complex models, evaluation, and then actually saying, okay, determining what should you actually look at. So you can see here your loss curves and your accuracy curves for validation and training. So we'll talk about this next time. And I think this is kind of useful because then even if you don't do image recognition, I think this process is going to be very similar for a lot of people. Okay, cool. But that will be next time. We'll end it here. Question, Jessica?
I have a question, yeah. So if we finish, I mean, this sounds ambitious, so I'm not saying that I'm going to do this for sure, but it's something I keep thinking. But so if we finish early, does anybody ever go back and do more of these projects?
Oh, absolutely.
Okay.
That, I think almost every student I know who has graduated, has done at least improved their project they were working on, or done offshoot or another project that's like that. And I think that's important too, because think of it like an interview perspective, what they'll ask you is hey, what have you been working on? And the last thing you worked on was 2 months ago because you've been searching for jobs and not doing anything else. It's going to be harder to talk about certain things, and it's just helps to keep you fresh and stuff. And also, like, I think the newer stuff that you're working on tends to be the most exciting thing. So you're able to show that enthusiasm that you would bring to their company and everything like that. Interviewers, recruiters love when you can get really excited about something, because it means that you probably are going to be excited to work there. So yeah, but definitely, I think you guys will have plenty of time. And plus, there's so much to learn. Yeah.
Cool. Thank you.
No problem. All right, everyone. Well, I'll stop it here. It is Thursday, so yeah, feel free to message out if you guys have any questions. If I don't have a one-on-one with you this week, or I guess tomorrow, really, hope you guys have a great weekend, and feel free to message out if you guys have anything that comes up. Right.
Yeah, man. Stay away from those fires.
Yeah, it looks like it's getting better for me, but there's still a lot of Big Basin. I love Big Basin, and it's like completely burned, like the headquarters and everything. Thankfully, the trees are good because they're redwoods, but the infrastructure for the camp is probably not going to be. I'm not going to be visiting there anytime soon, which is unfortunate. But I don't know. I'm pretty blessed where I am right now. Like, it could have been. There's a lot of people who are in a lot worse positions than I am. So, yeah.
Good to hear.
Thank you. All right, take care, everyone.
All right, you too.
Take care. Bye.
Bye.